Our focus today is on Unit 3 of the Web Technology track, specifically examining the architecture of Java servlets and XML. A modern web server operates in constant bombardment. At any given second, it processes thousands of dynamic connections from browsers across the globe. At the center of this traffic sits the server container. It acts as the anchor, receiving these raw HTTP requests and determining how to handle them. To process these inputs, the container relies on a Java servlet. Servlets act as the programmatic middle layer, connecting incoming requests from a web browser to back-end databases and dynamically generating the response. But operating at this layer introduces a serious engineering challenge: concurrency. The server must handle thousands of these dynamic requests simultaneously, without exhausting the underlying hardware. There is also a second major problem. The HTTP protocol itself is entirely stateless. It has no built-in memory. By default, every time a user clicks a link or submits a form, the server treats the incoming packet as a completely new, unrecognized client. Java servlets are engineered specifically to resolve these two opposing problems. They achieve hardware efficiency through a specialized threading model, and they establish user persistence through dedicated session management APIs. In the legacy CGI environment, every incoming HTTP request spins up a separate, heavy OS-level process. This creates a fatal bottleneck. Creating a new process for every single request consumes immense memory. Under heavy load, the server quickly breaches its hardware limits and fails. The Java servlet container solves this by abandoning process creation entirely in favor of a thread-based execution model. When a container deploys a servlet, it loads it into memory exactly once. For every subsequent client request, the container generates a separate, lightweight thread that maps directly to that shared servlet object. Generating a thread requires only a fraction of the computational overhead compared to spinning up a full operating system process. Because it avoids building an isolated environment from scratch for every hit, the servlet model operates significantly faster than legacy CGI. However, this efficiency comes with a trade-off. Because concurrent threads share the same memory space within the servlet object, any attempt to read and write shared variables requires explicit programmatic synchronization. By shifting workloads from heavy OS processes to lightweight internal threads, servlets eliminated hardware bottlenecks, transforming the server into a highly efficient shared memory environment. To execute this threaded model safely, the server follows a strict chronological sequence from the moment a URL request arrives. This flowchart maps the servlet lifecycle state machine. Step 1 occurs when the server receives the first HTTP request. It dynamically retrieves the servlet, loads it into the address space, and invokes the init method. Invoked only once, it configures the servlet. Step 2 is execution. The container invokes the service method for every active request, acting as a router to direct the data payload. Finally, upon shutdown, the server calls destroy to halt threads and relinquish resources. Once the destroy execution finishes, the memory allocated for the servlet object is marked for garbage collection. This three-stage lifecycle ensures that the servlet operates as a persistent, reusable entity. By separating the initial setup from the per-request execution, it drastically minimizes the response time for all subsequent users. But executing the request rapidly is only half the battle. Because HTTP is inherently amnesiac, the server still views every interaction within those threads as a blank slate. Developers use a 4-quadrant session tracking matrix to recognize users. First, cookies, tokens stored in the browser's cache, either non-persistent or persistent until logout. Second, hidden form fields, invisible HTML input tags that transmit their value to the server's getParameter method upon submission. The drawback is rigidity. Embedding session IDs fails on static HTML pages without hard-coded values. The third method, URL rewriting, fixes this. A token with a name-value pair separated by an equal sign is appended directly to the hyperlink. This URL fallback works if browsers disable cookies, but requires clicking a link and only transmits plain text. The final method is the HSession interface. Using the getSession API, the server creates a dedicated memory block, tracking precise creation and last access times. These 4 techniques offer a spectrum of architectural choices, allowing developers to trade off between lightweight browser-side storage and highly secure server-side memory allocation. This architectural map combines these concepts into the complete servlet execution pipeline. It begins when an HTTP GET request, carrying a URL rewritten token, hits the server. The container accepts the request and immediately allocates it to an active, lightweight thread within the existing process space. That thread passes the data to the service method, which routes it directly to doGet. The method then programmatically extracts the appended session token. The token maps directly to an existing HTTP session object, providing the servlet instance with the specific attributes stored from previous requests. Armed with both the incoming parameters and the historical state, the servlet generates a dynamically customized response and writes it back to the client. All of this complex routing, data extraction, and memory mapping happens in milliseconds, allowing a single server process to manage thousands of concurrent identities without collapsing. Servlets achieve high throughput using efficient threads and maintain context by binding HTTP to dedicated tracking APIs. Mastering this pipeline, from the thread-based lifecycle to the integration of session APIs, provides the framework for high-performance applications, maintaining user context at any scale.